Ever wondered about the logistics of snapping a picture of our very own galaxy, the Milky Way, particularly when we're situated right in its heart? This intriguing question isn't just unique to you. It has ignited curiosity in many, from the everyday person to the most accomplished astrophysicists. Let's delve gently into the cosmic pool to unravel this mystery together. The Milky Way, our cosmic neighborhood, is an expansive, bustling city of stars, gas, and dust. It is a barred spiral galaxy, a unique configuration that features a central bar-shaped structure composed of stars. This central bulge is encapsulated by four major spiral arms: the Norma arm, Scutum Centaurus arm, Sagittarius arm, and Perseus arm. These arms are essentially streams of stars swirling outward from the bulge like cosmic pinwheels. It is within these arms that new stars are born, their birth signaled by the radiant glow of nebulas. The Milky Way's visible diameter spans between 150,000 and 200,000 light-years, hinting at its colossal proportions. It is estimated to contain 400 billion stars and over 100 billion planets. Furthermore, the Milky Way is part of a galaxy group known as the Local Group, emphasizing its enormous scale. Such enormity is such that light, the thing known to us, takes a staggering 100,000 years to traverse from one end to the other. To navigate within this sprawling star city, astronomers use a system akin to Earth's longitude and latitude, called galactic longitude and latitude. Galactic longitude is measured along the plane of the galaxy, while galactic latitude measures the angle north or south of that plane. The sheer size of the Milky Way drives one to contemplate the challenge of capturing a comprehensive picture, especially when you're right in the middle of it all. It's comparable to standing in the heart of a vast forest, attempting to capture the entire wilderness in a single snapshot. Seems impossible, right? But brace yourself, as the explanation is way more intriguing than you could surmise. To grasp the concept of capturing images of the Milky Way, we first need to comprehend its incredible scale. Let's immerse ourselves in the vast cosmic expanse that we know as our home, the Milky Way. Visualize a city filled with stars, an enormous metropolis that's hard to fathom. Now multiply this by 400 billion. Indeed, our galaxy is estimated to be home to this astounding number of stars, a quantity so gigantic it almost becomes an abstract concept due to its vastness. But stars only form one part of the equation. Now we need to consider the physical size of the Milky Way. It's shaped like a disk, stretching approximately 100,000 light-years in diameter from one edge to make it more tangible. If you were to travel at the speed of light, crossing from one side of the galaxy to the other would take you 100,000 years. This is where the concept of light years comes in. A light year is the distance that light travels in a vacuum in 1 year, which equals approximately 9.46 trillion kilometers. To add another astronomical unit, parsecs, a parsec is approximately 3.26 light years. Beyond diameter, let's touch upon the Milky Way's depth. The galactic disk isn't flat. It has thickness, about 1,000 light years. Hence, a light-speed journey from the top to the bottom of the disk would last for 1,000 years. At this point, it's essential to discuss the mass of the Milky Way. It's estimated to be around 1.5 trillion solar masses. And this includes not only stars, but also dark matter and gas. Surrounding our galaxy is an invisible halo made up of dark matter. This mysterious substance, which we cannot see but detect through its gravitational effects, makes up most of the mass of the galaxy. Let's delve deeper into our galaxy's core. At the very heart of our Milky Way resides a supermassive black hole named Sagittarius A*. Its mass is approximately 4 million times that of our Sun, and it plays a crucial role in the dynamics of our galaxy. Now, where does our solar system fit within this galactic cityscape? We're not at the epicenter. Instead, we dwell in the suburbs, located about 26,000 light-years from the galactic core. We inhabit one of the spiral arms of the galaxy, specifically the Orion arm. Understanding the scale and complexities of the Milky Way is akin to decoding a cosmic map. It places us within the vast universe and facilitates our understanding of the colossal task we have undertaken. We're not merely capturing a snapshot of our backyard. We're attempting to seize a panoramic view of a sprawling city of stars, dust, and gas, complete with its dark matter halo and a supermassive black hole at its core. Recognizing our position in this cosmic metropolis is a crucial step to capturing its grand portrait. So, how do we capture the universe from our limited perspective within it, particularly something as colossal as the Milky Way? In contemplating this puzzle, we explore the realm of cosmic photography, a discipline that pushes the boundaries of human invention and comprehension. Astrophotography, in its most basic form, is akin to creating a masterpiece with one eye shut and your hands bound. It's a mission fraught with challenges, each more intimidating than the prior one. First and foremost, we confront the obstacle of light pollution. Our urban, suburban, and even rural areas are drenched in artificial luminance, obscuring the dim light of distant stars and galaxies, and posing a significant obstacle to any cosmic photographer. Another challenge is Earth's atmosphere, our protective shield that paradoxically obstructs our cosmic view. Similar to the ripples created from a stone's throw into a pond, which distort the reflected image on the water surface, our atmosphere bends and twists the light from celestial bodies, a phenomenon known as astronomical seeing. Another aspect is the extraordinary distances involved in cosmic photography. The light rays we record from remote stars and galaxies have journeyed across the vast cosmic void for millions, possibly billions of years. This implies we are capturing not just images but glimpses of the distant past. To conquer these obstacles, humanity has dispatched an array of satellites and telescopes into the deep beyond. From the Hubble Space Telescope, an optical telescope orbiting Earth, to the radio-equipped Voyager probes now in interstellar space, each tool has contributed to our knowledge of the universe. Optical telescopes like Hubble allow us to see light in wavelengths visible to the human eye, whereas radio telescopes, like the Voyager probes, can detect radio waves, a form of electromagnetic radiation with wavelengths longer than those of visible light. Then, we have infrared telescopes which detect heat and are often used to study celestial bodies obscured by dust and gas clouds. Each type of telescope plays its role in piecing together our cosmic puzzle. Yet, capturing a comprehensive image of the Milky Way, a swirling mass of stars, gas and dust, spread over 100,000 light-years, remains an extraordinary endeavor. Despite our microscopic viewpoint within it, the answer lies not in a single snapshot, but in assembling a cosmic jigsaw. The image of the Milky Way that we're accustomed to is not a singular snapshot, but a blend of numerous images. Unfolding this mystery takes us into the intriguing realm of cosmic photography. Envision a massive jigsaw puzzle. Each piece corresponds to a snapshot of our galaxy procured by various telescopes. This is the process behind assembling our view of the Milky Way. A significant contributor to this imagery patchwork is the Hubble Space Telescope, a forerunner in celestial exploration. Since launching in the early 90s, Hubble has been relentlessly surveying the universe, filling our archives with countless images. However, these pictures are more than visually appealing. Each one is a data mine brimming with information about the celestial bodies that form our universe, from stars and nebulae to galaxies. Hubble, though crucial, is not the lone ranger in this exploration. We also have the Gaia mission, a project by the European Space Agency that's dedicated to mapping our galaxy in 3 dimensions. Since its inception in late 2013, Gaia has been continuously gathering, processing, and analyzing an astronomical amount of data. To put it in perspective, its latest data release encompasses precise measurements of almost 2 billion stars. But how do we take these images and data and form the familiar image of the Milky Way? This is where image processing and data analysis come in. It's a complex task that calls for the expertise of many scientists and astronomers. They meticulously merge these images, considering the position, brightness, and color of each star. They use software algorithms to analyze and interpret the data, identifying patterns and anomalies. Large datasets are processed using supercomputers, and artificial intelligence is leveraged for accuracy and speed. This process is much like weaving a grand cosmic tapestry, with every thread symbolizing a piece of data. The end product is an intricate, stunningly beautiful portrayal of our galaxy that reflects the contribution of numerous space missions. However, what about the center of the Milky Way, the part shrouded by dust and gas? Well, that's where radio astronomy comes into play. It has the unique ability to penetrate these cosmic veils, offering us a special view of the galaxy's core. The story of how we map this obscured center is equally fascinating, but we'll save that for another time. For now, let's appreciate the marvel of cosmic photography and the awe-inspiring beauty of our Milky Way. Radio waves, a type of electromagnetic radiation, have the unique ability to penetrate the dust and gas that obscure our view of the Milky Way's core, making them an invaluable tool in astronomy. Just imagine possessing a superpower that allows you to gaze through cosmic dust and gas, right into the heart of our home galaxy. This isn't mere fiction, it's radio astronomy. Since the mid-20th century, radio telescopes have been acting as our windows to the invisible cosmos, our gateway to the unseen celestial bodies. This isn't a solitary quest, but a collective effort involving a global network of over 60 radio telescopes, located everywhere from the vast plains of New Mexico to the isolated heights of the Chilean Andes, and from the arid deserts of South Africa to the frosty expanses of Russia. These diligent cosmic investigators, the radio telescopes, are ceaselessly gathering data. Over the years, they have accumulated a staggering amount of information. We're talking about petabytes. To put it in perspective, that's millions of gigabytes. But this data isn't merely numerical. It's a language that provides insight into our galaxy's structure and composition. It creates a vibrant image of a thriving cosmic metropolis, teeming with stars, nebulae, and possibly a supermassive black hole at its center. Interpreting this language, converting the unseen into the seen, is a formidable task. It requires intricate algorithms, potent supercomputers, and the collaborative intellectual prowess of thousands of astronomers and astrophysicists across the globe. Their efforts have culminated in a stunningly beautiful map of our Milky Way, a radiant testament to human innovation and our unquenchable thirst for understanding the cosmos. So the next time you examine a picture of the Milky Way, reflect on the extraordinary journey of scientific exploration, technological advancement, and sheer volume of astronomical data that has made such an understanding possible.